anytime if you have any questions or thoughts that you would like to share. Right? So with that, let's get started. So Mayuri, I am audible, right? Clearly, and my screen is also visible, isn't it?
Yeah, yeah. Your screen is visible and you are audible clearly.
Awesome. Thanks a lot. Let me start with a quick history of AI and ML, right? So you may be aware of many of these things, but just to set the context here so that we see how this field has evolved. Uh, Way back in 1930s is when a guy called Alan Turing introduced what we know as today's computers, right? So it has an input device, which is an input tape, paper-based tape. Then there is a computation block. Then there is an output paper-based tape again, which would serve as memory as well. So that was the beginning of the abstract computation model somewhere in the late 1930s. And then the same guy again in 1950s went on to build something or come up with a definition of something which is called the Turing test. Right? Now, Turing test is essentially the definition of how can we say that that a machine is exhibiting some sort of an intelligent behavior and is equivalent to human. So he had put that in a very clear, simulated way, well, sort of gamified it, right? So that's what Turing test is all about, and that holds a lot of relevance even today in many of the AI systems that we build. And then in 51, neural networks, which is one of the most popular and most fascinating topics today. The first neural network in its very basic form was built by Minsky in 1951. It is not, or it was not as sophisticated as the ones that we see today. It did not have too much of learning capabilities as well, but it all started in 1951. Then somewhere around 1956 is when we were introduced to a computer program called Chinook, right? And this was the first man-to-machine program which played checkers, right? So it was a computer program that could play checkers with human being. And the reason why it became famous was because it went on to defeat the reigning checkers champion. Now, for all of you who don't know checkers or are not familiar with checkers, it's a board game. In a very crude sense, it's like a grandfather to chess, right? So it was developed way back and it's way simpler compared to chess, but it's still a board strategy game, right? And this program Chinook went on to defeat the reigning champion in checkers, and that's what caught the fascination of people in terms of what machines can do and what intelligence they can inherit. And after that, there was a lot of investment with regards to research in the AI space. And most of this research was predominantly in the rule-based system, especially in the natural language processing space, driven by the Turing test. So people were focused on building interactive systems, chatbots predominantly, which had some understanding of the language but were driven by rules-based systems. So that's where you would see systems like Eliza come up during those 20 years. And Eliza, by the way, is again a chatbot. If checkers is the grandfather for chess, then Eliza probably is the grandmother for Alexa, right? So that's what had happened during the next 20 years or so. And then from 1970s to about 1990, early 1990s, uh, all of a sudden the interest in AI dipped, right? And this was primarily because people started having doubts about the complexity which these systems can acquire. Minsky's neural network failed to scale. Eliza had a lot of rules, which were also very difficult to scale with regards to deep conversations that it was expected to have. So people started having doubts in terms of the real power or potential of AI. And so for almost 20 years, except for one or two events that you see here in 1982, AI was a bit low during this time. And then again, somewhere around 1997, another fascinating event happened, which was another man-to-machine game. And this was on the chessboard, and it was between Deep Blue, which was a supercomputer, and the reigning chess champion, that is Gary Kasparov. Right. Deep Blue, by the way, was a C program which runs on AIX, and it had like 30 odd computers doing parallel computing. It had special VLSI chips that were designed for alpha beta pruning algorithms, which are specifically gaming based algorithms. So it was a very specially designed and extremely powerful system. And it was pitted against the reigning chess champion. Now, it did win the first game. So Deep Blue was the first computer to defeat a human chess champion. So it won the first game, but then it went on to lose the next three games, and the remaining two games were drawn. So it lost the series, so to say, in 1997. And then in 1998, again, it came back to win the series and defeat Gary Kasparov. So Deep Blue essentially became the first computer to win the chess game, one game, and the whole series as such, right? So that again triggered a lot of interest in AI. A lot of people started again fast, imagining what AI could do, what is the potential, and then money started flowing in again. But one key thing to note here was that Deep Blue was still a very rule-based and search-heavy system, right? So it won because of brute force computing power, not because of the sophisticated AI that we see as of today. And one of the first instances of the kind of AI that we are seeing today happened in 2005 in what we call the DARPA Grand Challenge. And this was the first time that we saw an instance of an autonomous vehicle, self-driving autonomous vehicle, like the ones that are becoming very popular today. So essentially, this was a challenge, and you should, whenever you have the time, go and check out YouTube for Stanley and AI autonomous vehicles. You will get videos ranging from 10 minutes to probably, I think, 2 hours or so. And it talks about the whole challenge and how the system was built and how the car went on to win the race, right? But essentially, this is a challenge where the participants are expected to navigate a very complex course, right? And this complex course is not 5 or 10 kilometers, it is actually 132 miles. And this whole course goes through desert. I think it's Arizona desert. It goes through the desert. It has a lot of steep climbs, U-turn bends, and so on as well. So it's an extremely complicated course. Uh, Humans, once the race starts, are not allowed to interact with the machine in any way. So once it goes off the starting point, then the car is on its own and it has to reach the finish point. And there were about 43 participants. Stanley was the car that was put forward by Stanford University, I think, and it went on to win the race. And then I think the second and third were from CMU. The two cars that came second and third were put forward by CMU. So a lot of research had gone into these kind of cars. But what made it interesting was that this was the first instance where it was, or we built a system that was a mix of robotics combined with LiDAR sensors and so on, computer vision, and machine learning or neural net based learning as we see today, right? So this was one of the first successful and complex instance or implementation of the kind of AI that we see today. And we started seeing glimpses of it somewhere around 2005 in terms of actually materialized products, right, outside of research. Then in 2011, many would have heard of Jeopardy, where Watson went on to win the quizzing game against two of the leading contenders. And the reason why this is complicated is because the machine had to come up with answers to very specific questions within fractions of seconds or milliseconds, right? It was against the buzzer race with humans. And it was not just like searching millions of documents and coming up with search results, like Google search results, right? You had to come up with one answer, which had to be the right answer. And depending on the confidence of that answer, you could press the buzzer or not, right? So it had to be very precise, and most of it was driven by deep learning and um, machine learning based algorithms. And then in the most recent instances, I think we have all heard about AlphaGo, which is a system from Google that went on to defeat Lee Sedol, who was the reigning or arguably the best player in the Go game, right? And interesting thing over here with regards to AlphaGo is that it was one of the first systems where Google was able to demonstrate a very complex task by making it a combination of reinforcement learning and deep learning. And Alpha Zero actually mastered the game better than anybody in the whole world within 40 days, right? So, what human Go players take years and years to master, AlphaGo or Alpha Zero actually mastered in just 40 days, but 3 days to learn what humans or reach the levels of human proficiency. And then it started playing with itself, and in 40 days, it had virtually become unbeatable, right? So that's a quick overview of how AI evolved, and mm, with examples of some interesting events or glamorous events that we would have heard in media, right? But behind these, the underlying algorithms or the underlying system complexity also was increasing as we saw through various applications of these systems, right? So that was a quick history of how AI evolved. So now let's take a look at some of the common terms that we come across, right? So you would have, see, essentially, we are all consultants here in the AI space, right? And we keep coining fancy terms. So you would have heard a lot of terms like artificial intelligence, machine learning, deep learning, cognitive computing, data science, advanced analytics, and so on. Now, all of these terms have a broad definition, but the boundaries are a bit vague, right? So many a times what happens in the industry is that they are used pretty much interchangeably. So don't, a piece of advice is don't waste your time arguing over specific definitions of these terms. They are pretty much used interchangeably, though there are subtleties to some of these definitions, right? So let's take a quick look at some of these definitions, and then we will move on to maybe applications and so on, right? So artificial intelligence is, according to one of these definitions, the broad superset of all the systems that can learn, act, and reason in order to help humans take decisions, right? Now, the earlier set of artificial intelligence systems were predominantly rule based. Experts had to find or feed in these rules or provide these rules that were fed into the system. And then the systems would execute the rules and help humans in terms of taking partial decisions. The systems were still not capable of taking decisions on their own. So that was the earlier set of artificial intelligence systems. Now, within this broad set of AI systems, there is a subset which we call ML systems, and these are predominantly algorithms, mostly statistics and probability based algorithms. And these algorithms are actually capable of going out, mining the data, and detecting patterns on their own. And so you don't need an expert now to come and tell you what are the rules on which decisions need to be made. These machine learning algorithms can go and find patterns and uh, make them or detect those rules themselves, right? Some of the examples of these rules or applications of these kind of systems were spam detection systems. They go to your inbox, or they can look at an email and say whether it's a spam or not. They can say, looking at a customer's buying history, whether somebody will buy a product or not. So those kind of decisions or patterns, these algorithms were able to detect on their own. Now, in the machine learning space, there is further smaller subset or a niche subset, which we call the deep learning algorithms. And these algorithms are complex implementations of a very specific machine learning algorithm called neural net. And deep learning algorithms are what are in the news or in the fancy as of today. And they are rightly so, right? Because they can perform a lot of complicated tasks. They can look at unstructured data. They can detect objects within images and videos. They can do facial recognition. They can do speech recognition, and so on. So that's the set of algorithms which has come up fairly recently and is extremely powerful, but it is a very special or detailed implementation of neural networks in particular, right? So that's one way of looking at how various terms fall in place depending on the complexity of algorithm as we move from left to right. Now, another way of looking at all these terms that you would come across in this AI space is with regards to how these systems learn. So you will come across algorithms that are called supervised learning algorithms, and these algorithms essentially learn from historical behavior or historical data, and then they are used to predict the future in terms of time series forecasting. So you see the sales figures for the last 5 years, and then you are able to forecast what's the sales figure going to be for your next quarter, right? So these are supervised algorithms that learn from prior history to predict the future. Then there is another set of algorithm, which is the unsupervised learning algorithms. They don't look at historical data per se, or they don't look at data as history, and they don't try to predict the future. But what these unsupervised learning algorithms do is they run through the entire data set, which can be millions of data points or millions of rows in your database table. And then they try to group similar looking data points together. And that is what we call clustering algorithm. So it can look at 1 million of your customer database or subscriber database, and then it can say 250 of this subscriber database is young customers who are using high-end mobile phones, extremely affluent using data. 150K or 15% of the customer base is senior citizens living in tier 2 cities, predominantly dependent on incoming calls and so on, right? So it's able to identify these groups from a larger data set. So that's clustering. And then unsupervised learning can also be used to simplify some of your machine learning problems by reducing the number of variables that you can look at. So these are examples of unsupervised learning. Now, there is a third set of algorithms, which is called the reinforcement learning algorithms. And these are essentially used in situations where you have a limited set of data to learn from, but that's not sufficient primarily because your environment is constantly changing, and you also need to adjust your learning depending on the new situations that you're seeing. And in order to model or in order to build systems that need to operate in this kind of evolving situations, you use reinforcement learning, right? And typical applications are gaming AI, like I mentioned. AlphaGo uses reinforcement learning pretty extensively. It is also used in robotics and so on, right? So this is another way of looking at how or another way of looking at the various terms that come up in the AI space or AI domain based on how algorithms learn from the data. Now, that was a quick introduction of some of the common terms that you would come across in the AI space, but there is also another topic that we can talk about before we look at projects and so on, is with regards to the process that is applied in the AI engagements or machine learning projects, right? Typically, in any software project, you would have come across terms like waterfall model, agile model, design thinking, things like that. And they are processes which are used to deliver complex engagements where it runs through multiple months or years together. There are 50, 100, 200 developers working on it. So you need a process to make sure that you meet your milestones and deliver the project over time. Now, those traditional methods don't apply to machine learning engagements. So you have to look at specific methods that are or processes that are relevant to the ML engagements. And one such method is what we uh, very frequently use called the CRISP DM. So it stands for Cross Industry Standard Process for Data Mining. And it essentially has about six broad phases. Um, I'm sorry. So it starts with understanding the business first of all, right? So if, for example, one of the telecom service provider calls you and says that I have a major problem, all my customers are leaving my network. Can you use machine learning to help me solve this problem? So the first step is in terms of understanding the business, understanding who these subscribers are, how do they get enrolled, what is the definition of leaving a network? Is it like somebody canceling his SIM? Is it in case of prepaid connection, somebody doesn't go and cancel the connection, right? He just stops using the SIM. So what exactly is the definition of somebody leaving the network, or what we call churn? So those are things that you would want to capture as part of your business understanding. After you have understood the business problem, then you move on to the next phase, which is called the data understanding. And this is where you would want to understand all the data elements that you would use for your machine learning project. Now, in order to predict if somebody is going to leave the network or not, you would want to know his usage, you would want to know his demographic profile with regards to his age, you would want to know details about his handset and a lot of other things, right? So who he is talking to, how well connected he is in your telecom network, how tightly integrated is he with the other subscribers and so on. So you would need all these data points, but if you go and ask the CIO or the CMO of Airtel or whichever network is popular in Surat, if you go and ask that service provider, I need these data points, he will not give you that, right? What he will typically do is he will throw a data mart or data center schema at you. And that is like a huge set of tables, 500 tables with a lot of columns in each of those tables, right? So you have to very patiently, working along with their data architects, identify which of these data elements, which of these tables, which of these columns within the tables give you the fields that you would like to use to solve your problem or do this analysis. So that is where you need to get a very good understanding of the data, and nobody will give it to you in a platter. It is a very interactive and very intense exercise that you need to do, working along with uh, the uh, data architects and CIO organization of the client. After you have got or identified the data points that you want to use, which is your data understanding stage, the next step is in terms of preparing the data. And this is a huge task, right? One of our professors used to say when I was doing my MBA that data preparation is essentially 90 to 95% of your data mining or machine learning project, right? The glamorous part of algorithms is just 5 to 10%, but 95% of perspiration happens in the data preparation stage. It's only 5 to 10% of inspiration that comes from the modeling phase. So a lot of work goes in the data preparation stage. And what you do over here is you look at the data, you find the quality of the data. Are there too many missing fields? How do you impute or how do you fill those missing fields? what is the granularity at which you want to do your analysis. So if you want to do your analysis in terms of telecom usage, the CDR data is typically at a second level, right? So you will have CDR records that capture data at each second. So do you want to do analysis at second level, in which case it will be enormous, immense. So do you want to aggregate it at maybe hourly level? So how many minutes in an hour did I use my phone? Or do you want to aggregate it at a day level? So how many minutes in a day did I use my phone? So you have to take those kind of decisions with regards to, sorry about that. So you have to take those kind of decisions in terms of how you prepare your data for analysis or modeling. And once you have done that, then comes the interesting stage of modeling, where you start applying these algorithms that we saw, supervised learning algorithms, neural networks, deep learning networks, and so on. And you build your model that is able to predict whether somebody is going to leave the network or not. And once you have built the model, then comes the evaluation stage, because your model needs to be effective, right? You cannot build a model where you start saying everybody is going to churn, because there is a cost associated with it. Organizations or service providers would want to give discounts or promotions to people they want to retain. So you need to have a good quality of model and a very high accuracy in terms of what you are predicting as churn. So there is an evaluation stage where you see how good your model is. And if you and the business agree that the model is accurate enough, then you move it to production, where it kind of continuously runs and starts generating this scores, right, or probability to churn. So this is how a typical machine learning engagement would look. These are some of the broad stages, but the outer circle indicates that it is an iterative process, right? So many a times what happens is you would do all the 5 stages, right from business understanding to evaluation, and then you will find that the model is not good, accuracy is very poor. So what do you do in that case? You essentially go back, try to understand whether there is a mismatch with regards to how you have defined your problem. You go and look at the data mark to see if there are additional fields that you can bring into the model, which can increase your accuracy. And then you try out maybe other algorithms, more complicated algorithms, to see if you can improve your accuracy score. So it's kind of iterative and it goes in circles till you achieve or reach the desired level of accuracy. Right? So that was about the process. And one of the most important gospel truth about machine learning and AI is that it is all about data. So your AI algorithms, your AI models are only as good as the quality of the data that you train them with. If your data is garbage, then your model outputs will be garbage. So it's a typical case of garbage in, garbage out. So you have to spend a lot of time, especially in the data understanding and data preparation stage, to ensure that you are working with extremely high quality, relevant data to build a good model. Right? So that is a quick introduction of some of the concepts of AI. So I'll stop here for any questions or any thoughts that you may have before I move on to the next set of slides. So we can take some questions if you have any here. And if there are none, then I can continue with the presentation.
I have a question. Hello.
Yeah.
Audible?
Yes, you are.
Yes. Yes, sir. So my question is that lately I've been reading a lot of articles that data science is just a fad and it has been going on for a long before the term data science was coined. So what are your views about it? Is it just another fad, or is there some ground? Uh, is there some concrete base to this industry or this field?
Yeah. May I know your name, please, also?
Ninad, sir. NINAD.
Ninand. Okay. Excellent question, Ninand. And one of the most popular questions, right? Especially for people who are at the cusp of taking decision in terms of entering data science or not. So you are right. And that is what we saw in some of the initial slides with regards to history and with regards to AI MLDL slides as well, right? So AI has been evolving over time, and the definition and frontiers of what is called AI has been changing as AI has evolved. So during the initial stages, expert systems, which were predominantly rule-based systems, were called AI or data science. Then there were machine learning systems, statistics and probability-based systems, which were better than rule-based systems. They were called data science or AI. And now there are more complex neural network-based systems that are called to be the true data science uh, domain, right? So, and again, these are fancy terms, but their definition and their scope of um, complexity keeps changing as algorithms keep evolving. So that is the first part of your question. Now, with regards to the hype, right? It is true that AI has been through a hype cycle, and that is primarily because of a lot of articles that we see, and part of it is also because of many of the tech companies that try to play up the potential of what AI can do. So there is some amount of hype. I would not discount it, or I would not deny it. But AI has been growing. The potential of applications of AI has been growing, and it will continue growing as long as there is improvement in the compute power, as long as the availability of data increases. Research funding will continue to flow in terms of improving the AI algorithms, and the applications of AI will keep on increasing, right? So if 5 years, 10 years before, if you look at self-driving cars was maybe just a very research subject, very restricted to maybe defense academies and so on. But now we are seeing it to be more and more commercial. People are taking tests out of it. Tesla, for example, has a self-driving module, though in many states you still need to have your hand on the steering, even if you put it into a self-driving mode. So those are becoming more and more commonplace. AI is, I would say, meeting up to its hype, but it will take some time before we reach what one of the more common terms, and one of the reasons why this hype is existing is because of a term which is called artificial general intelligence, right? AGI. And that term is basically an indicator of machines can have general intelligence. They don't need to be trained for a very specific task in terms of face recognition or in terms of driving, object detection, and so on. Machines can get artificial general intelligence just like humans. That is still far away. We will not reach there anytime soon. Even completely autonomous self-driving cars, we will not reach there anytime soon. But we will take significant steps towards getting there. There will be a lot of progress that will be made. So did I answer your question, Anand?
Yes, sir. You do.
Thanks. Great question. Thanks for that. Huh? Okay. Any other questions? Otherwise, we can move on to the next set of slides. Okay. All right. So let me go back to my presentation. All right. So let's see. Yeah. Okay. So one of the ways we saw various classifications of AI based on the algorithms, but the way I look at AI is predominantly based on the input data. So as we saw in the previous slide, right, data is the most important element of AI. So I typically like to structure my AI projects or AI engagement depending on the data that I'm going to get. So a lot of problems revolve around structured data analytics. So this is typically data that is there in database tables. Then there are problems that deal with image analytics. So usually the client gives you a set of images or videos, and then you are supposed to infer something from that. Or it is predominantly text-based analytics, where you have to do natural language processing on a huge volume of text coming from websites, blogs, textbooks, and so on. Or it could be audio, speech-based systems, especially those that engage in conversations like Alexa, Siri, and so on, right? So I typically like to classify my problems into these four broad buckets based on the type of data that I am going to analyze. So now let me quickly talk about some of the structured data problems. I don't want to go into algorithms per se, because you would anyways have it in your theory classes, but typical structured data algorithms are regression techniques, decision trees, support vector machines. Then there are clustering algorithms like k-mean, principal component analysis, and so on. Don't worry too much about this for this particular presentation if these are not very familiar terms, but you will hear about this when probably you start taking courses or going deeper into machine learning. But these are some of the algorithms that are applied for structured data analysis, right? Now, one of the engagements that we did in structured data analytics was around campaign management, right? And this was essentially for large companies, large FMCGs like Procter and Gamble, Unilever, PepsiCo, and so on. So these are huge MNC FMCG companies, fast-moving consumer goods, right? So, and they have thousands and tens of thousands of products or SKUs, right from food products to cosmetic products to medicinal products, and so on. So they have a wide variety of products and many, many SKUs within each product line. So essentially, it is very difficult for a brand manager who is owning a product line to come up with a campaign strategy that is very optimal. Campaign management, by the way, is an art and science in itself, especially in the marketing domain. And what these brand managers do when they are coming up with their campaign strategies is they try to come up with a regional strategy, right? And a significant amount or a major contributor to this regional strategy is the sales numbers of specific region. So if you are, for example, we did this for the ice cream product line of Unilever. So if you are the brand manager for the ice cream products or dessert products of Unilever, then you would get sales figures and you would try to come up with strategies which say that northwest region of the US has not so great sales of ice cream. So I will put a campaign over there with regards to coming up with discounts for my ice cream products. Northeast, not selling at all. I don't want to invest anything because ice creams are not the product there. It's extremely cold in that region, for example, right? Whereas Central South, I have extremely high competition, so I need to, my sales number reflect that. It's average, not too less, not too high, but I need to do something with regards to keeping up with the competition. So I have to come up with a sales strategy for this particular yellow region. And maybe towards Southwest, I have the monopoly. I don't have to worry about anything. My sales numbers are extremely good. So I will come up with no specific campaign in this region. So essentially, the point that I'm trying to make is usually these brand managers and campaign managers come up with regional planning. Now, what happens with this whole regional planning approach is that there are stores within each region. Some store probably in this region, which is not doing so great. Maybe there are neighborhoods where stores are doing extremely well in terms of Unilever ice cream sales, but on an average, they are not doing great. right? So if you apply a blanket regional strategy, it will apply to stores that are doing well as to stores that are not doing so well. So it is kind of suboptimal. So the approach that we tried to build is what we call hyperlocal planning, where you go away from this whole regional aggregate kind of planning and you try to make it more localized at a store level or a store type level, right? So that's what we mean by this whole hyperlocal planning. And when you start doing this kind of hyperlocal planning, the advantage of that kind of planning is that you start asking questions in terms of why is this particular store doing so well? Is it because of its location? Is it because of people staying there? Is it because of the layout of the store and things like that? And then you get more insights in terms of what are driving the sales for a product line. So hyperlocal planning, one, helps you optimize your campaign strategy, plus it also gives you more insights in terms of what works and what doesn't work for your product. Now, the way we went about doing this is by collecting a lot of data. So we did this for the London region. So there were about 1 lakh stores in London. We went about collecting data for these 1 lakh stores that use to stock Unilever ice cream. And we collected data from all kinds of chains, right? We went to Tesco, we went to Sainsbury, we went to convenience stores like Waitrose and so on. And we started collecting data, sales data from all these stores. We started collecting the competitor data, point of sales data, as well as any data related to layout of the stores, channel data around the stores. And we got this data from data providers like Nielsen and so on, right? So that's one source of input that we got. The second source of input that we got was with regards to the social media feeds that Unilever was able to procure for us for this particular region. And we were able to get some insights with regards to personality of people who were consuming their products. We were able to look at some amount of sentiments that were getting generated around their products and so on. So that's the second type of data that we were able to gather. The third kind of data that we looked for was with regards to the demographics of the city itself. So this is published demographic that is available in many of these government portals, and then there are agencies also from where you can buy this data. So we collected data about neighborhoods in the London city, right? And we call those units as wards. So data about what is the average density of population in a neighborhood, what's the average age, income, maybe average house size and things like that, crime rate, all those different things about neighborhood that we can collect. So that's the third kind of data that we were able to gather. And then we also looked at external events like weather. So what has been the weather in London city and how it has been impacting the sale of ice creams in each of these neighborhoods over a period of time, 1 year or so. What were the various events that happened? So if was there a football event or a concert that was happening in some neighborhood, because of which there was a lot of footfall, because of which the sales of ice cream went up, right? So we collected those kind of external events or external factor data as well. So these were some of the feeds that we were able to gather. So there were about, I think, 5, 7 dimensions of data that we were able to get. And we combined all these different data points to come up with a consolidated set of features. So I think we had about 500 plus different features from all these 5 or 7 different dimensions that we were able to gather. And using these features, what we tried to do was we tried to profile the stores and the wards or the neighborhoods. So 2 sets of profiles. We tried to find out sets of stores that looked identical to each other. So there may be a set of stores that had very similar store size that probably were either convenience stores or supermarket stores or some such kind of similar type of stores that were being run predominantly maybe by senior citizens or maybe by college students who were doing stretch work to get some extra pocket money. So we try to group stores based on these attributes, and that is what we call the store profiles. And we were able to get, I think, about 50 plus different store profiles. And we did similar profile mapping for the neighborhoods as well, and we called that the ward profiles. So now we have two sets of profiles, a set of store profiles and a set of ward profiles. And then we tried seeing interactions between store profiles and ward profiles. So within a neighborhood, there could be multiple types of stores. So there could be a store with store profile A, there could be another store with store profile B. And what we tried to see is in a ward X, which of these two types of stores was more successful and why, right? So we were able to then correlate interactions or compatibility of store profiles to ward profiles. And using that, we were able to come up with some actionable insights that we were able to give Unilever. Now, what you see in this next slide is some of the insights and actions that we had proposed based on this whole detailed structure and analysis that we were able to do. One of the things that we found was the convenience stores were becoming more and more popular, right? And maybe it is intuitively uh, available to people who are local, but for a brand manager who is sitting maybe somewhere in Europe, he will not have this intuitive feeling. So for him, it needs to be shown through data. So we were able to show that convenience stores were becoming more and more popular. Footfall and sales in these stores were on a steady growth, whereas supermarket stores were not doing so great. So Unilever may want to change its strategy with regards to focusing more on convenience stores. We were also able to give a very specific set of segments in terms of people who frequented these convenience stores, right? So they were people who have extremely high salaries, they were working adults, and they fell into the high income bracket. And the reason why this was useful is because Unilever now got an idea or a picture of the kind of customers who were visiting these convenience stores, and they were probably doing it either on their way back from work or because it is closer to their house and they could just stock up things on need basis and so on. So that was one insight that we provided them in terms of changing focus. We also found that the health conscious segment was on the rise, but they were extremely picky about the products that they would choose, right? And it is not wise to ignore this segment because it is influencing other segments also. So we gave them very clear picture in terms of how the health conscious segment is evolving. They have their preferences for sweet and dessert products, but they have certain conditions when they go for these kind of products, right? So that's another thing that we were able to show. We were able to show how various brands were playing against each other, whether one of the Unilever brands was cannibalizing or eating into sales of the corresponding Unilever brand another ice cream product, or was it beating the competition? So we were able to show interplays between power brands. We were able to show sales were shifting away from weekend towards weekdays. So maybe their replenishment cycles or the way they stock up inventory in stores need to now not just focus on Saturday, Sunday sales, but also need to have some intermediate weekday replenishments also. And one of the other or more important findings was with regards to the store layout and channel layout. We were able to find out that certain kinds of store layout or certain kinds of product placements were extremely useful in terms of bringing up the sales. So we were able to show that kind of a correlation with numbers. And then make that as a standard guiding instruction or make that as one of the negotiation parameters for Unilever whenever it is getting into tie-up with some of these chains, right? So these were some of the decision points or insights that we were able to generate and influence based on the analysis that we had done using the structured data analytics. So now, let me see how we are doing on time. Okay, so let me just quickly cover image analytics also, and then we can pause for questions maybe. So the other type of input in that 4 dimensions that I was showing is image. And uh, in image analytics, one of the most popular techniques that we see today is the convolutional neural network, right? So it's a deep learning technique, very, very popular, and has been extremely effective in the recent days. Again, don't worry too much about the algorithm per se and some of the terms that you see over here. You will learn it over time. But one of the things that I would like to mention here is that a lot of these convolutional neural network models, you don't have to build them from scratch. You don't have to train these models from scratch. They are already available for you to use and retrain or configure for your specific needs. So if you look at the bottom left, there is ResNet, which is already available for Microsoft. There is InceptionNet available from Google. And then there are some of the other open source neural net CNNs also available like VGGNet and AlexNet. These are networks that have been trained on millions of images, and they are able to identify like 1,000 different types of objects like cats, dogs, humans, vehicles, trains, trees, sky, and things like that by default, right out of the box. And these are extremely powerful and accurate networks because corporations like Microsoft and Google have built this on huge amount of training data. And these models were built over many, many days or weeks of training on extremely powerful hardware. So typically what we do is we take one of these existing neural networks, we chop off some of the last layers that you see, and then we append those layers with new layers, and then we feed it our specific domain data, our images or our video feeds and so on. And then we try to learn only in these last few layers. And that is what we typically call transfer learning. And that reduces the training time significantly. Plus, it also gives you the benefit of leveraging all the learning that Microsoft or Google has already acquired in the preceding layers, right? So, long story short, CNNs are the most important or most popular methods in image analytics today. Don't have to build them from scratch. There are already available models. Customization of those available models can be done by chopping off some of the most uh, outward layers and customizing them to your specific needs, right? So those are some of the 3, 4 guiding principles that you can keep in mind for image analytics as of now. So now, what are some of the common use cases in image analytics? So one of the POCs that we did was with regards to looking at images from stores and finding out when does it need replenishment. So ideally, the way it is done as of today in many of the traditional retail analytics or retail field work is that somebody from each brand goes, he takes a look at the shelf, he finds out the stock levels, he talks to the store owner, he gets an idea of that, and then he uploads those forms using a mobile phone or using a web form to the central distribution channels, right? But instead of that, one of the retail chains or one of the product companies wanted to try out if image analytics can automate that whole activity to a great extent. So that was one of the proof of concepts that we tried. It is becoming popular. We are going through the subsequent stages in terms of refinement. Another very common use case is with regards to facial recognition. For those, it's extremely useful in terms of security, especially in COVID situations and all. We have been seeing videos in many of the firms, especially in China and so on, where they are using this to automate a lot of touchless entry and things like that. And then for people who have seen Minority Report as a movie, you would have seen ads getting customized depending on your facial recognition. That is still as Ninant mentioned, it's still far away, conceptual, but those are some of the applications around facial recognition. But an interesting use case that we did was for a couple of insurance companies, car insurance or vehicle insurance companies in India and I think in Germany. So what we did over here was that an insurance agent or somebody from the insurance firm actually needs to go and visit some of these damaged vehicles in order to assess the damage before the claims are approved, right? And what these insurance companies wanted to do was to see if a lot of this process can be automated, because then it would reduce a lot of manual effort, and it would also reduce some amount of subjectivity that these human evaluators or auditors would have. So we built the model in like three broad stages. So the first stage was with regards to identifying the car itself. So you try to find out in the image what is the car, what is the make and model of the car. So that would give you some idea with regards to how expensive the claim can be or how economical the claim can be. So that's the first step. The second step that we try to do is to find out where exactly on the car did the damage occur, right? So was it on the door? Was it on the window? Was it some of the headlights? Was it a bumper? Or was the wheel rim damaged and things like that? So we try to find out various regions of the car and which part of it was damaged. And then we try to find out the extent of damage in terms of high, medium, or low. And then we make or combine all these three parameters and come up with some sort of a approved claim amount or an estimated approved claim amount, which is then given to an assessor to see whether it makes sense and can be approved or not, along with all these evidences. So that automates the whole process to a great extent. Now, it's a different story in terms of how do the images come. That's a discussion that we have had with these companies. So uh, where things are easily available, labor is cheap. They say, yeah, the guy would now go and take pictures instead of making a full audit assessment form, and those would be the images that would be uploaded. In more tech-savvy countries, they were even open to the ideas of probably a drone just going there and taking the images and then sending those back, right? So how the images actually get fed into the system is something which is very subjective and would depend from provider to provider, country to country. But this whole model of assessment was pretty well appreciated, and it did help in terms of gaining a lot of cost savings in this whole process, right? The second use case that I would want to quickly talk about is with regards to one of the liquor manufacturing firms, right, Bacardi, and they wanted to find out what is the most popular cocktail brand or cocktail type that people usually prefer, and they wanted to have some sort of a split in terms of demographics. What are the drinks that men prefer? What are the drinks that women prefer? What is the general age of people who buy our products and so on? So this is an analysis that we did. Bacardi actually provided us with a lot of images that they had collected over time from their Insta feeds, from their Facebook and Twitter feeds, and so Twitter handle and so on, as well as some of the other images that they had collected offline as well. What we did was, from those images, as the first step, we identified the actual drink region, right? So that's what you see in the middle part. Then, based on the drink region, we extract some of the features like the color, the amount of ice, and things like that, which are there in the region that has been cropped. And then we try to go and look up those combinations in the database to find out what's the cocktail associated with those features in terms of image data that we have extracted. So that's a part of data extraction that was done. And then we go about doing some amount of structured and descriptive analysis. So what we were able to find out was, sorry, what we were able to find out was that there are certain cocktails that were very popular with regards to Bacardi products. So there was a Grey Goose based cocktail called Lefes, which was very popular. Smirnoff based cocktail, which was raspberry lemonade, that was extremely popular. We were able to find out what kind of glass shapes are popular so that they could use that more in their advertising, what kind of glass shapes have appealed. We also found out what brands appeal to men versus what brands appeal to women. So that again can be used in some of their marketing campaigns whenever they are marketing some of the brands. So if it's Grey Goose, they would have it more targeted towards their male consumers. If it is maybe Smirnoff, they target it more towards their female consumers, right? And then another thing that we were able to find out was in terms of the age demographics. So it's typically young folks who were heavy consumers of many of these Bacardi brands. Probably the older guys like their whiskeys and rums better. So that's one of the insights that we were able to gather from this particular analytics. Now, before I stop or pass over from the image analytics space, one of the things that we always need to keep in mind as far as image analytics is concerned is the ethics around image analytics, right? So there are a lot of incidents that keep coming up every day over and over again, right? One of the most popular incidents was with regards to the Uber car accident of the self-driving car that happened. Right now, there were many questions that were raised with regards to, is it ethical? Are models ready for self-driving itself? Um, who should be blamed? Is it the model's responsibility, or is it the data miner's responsibility in terms of training for these kind of situations? Was it the fault of the person who was behind the wheels? Should he have intervened sooner? Should there be statutory regulations or rules in terms of deciding these kind of parameters? So a lot of questions with regards to ethics around image analytics is still open. Another common problem is with regards to the bias, right? So if you maybe go to, maybe Google has fixed it now, but once upon a time, if you went to Google and then if you typed hands in their search box, all the images that came up were predominantly male white hands, right? And after that, somebody just did, it's just a random experiment that somebody was trying out. And after doing search for hands, he found that this is the kind of results. Uh, that person went and searched for black hands, right? And then most of the images that came up were very aggressive or derogatory kind of hand images. So that again raised a lot of questions with regards to bias in terms of how these images are getting identified and labeled, right? Apparently, it looked like if somebody just says hands, the underlying assumption is that any search is predominantly white based. If somebody adds the adjective of black, then there has to be some sort of a dark meaning associated with it. And that bias was implicit in the search results that came out, which apparently means that the image analytics that was running behind the search algorithms was also biased. Google, I think, has fixed it, but it raised a lot of questions, and because of which there are many organizations who are moving away from these use cases that can have heavy bias influence. IBM, for one, has started divesting or disinvesting in its facial recognition algorithm because it's heavily bound to bias as of today. And then we all know the kind of menace that deepfakes can have, right? They can cause a lot of political disturbance. They can disrupt business negotiations with a lot of fake information being put out. It can cause a lot of personal agony if used in the wrong way. So there are still many open issues and agendas around the ethics of image analytics, which we need to keep in mind when we are applying these kind of technologies. A lot of companies who are also building the underlying framework for image analytics are aware of it, and they have also started acting on it. Microsoft, Facebook, and a lot of companies, Google, IBM also for that matter, has started taking preventive measures against this misuse of image analytics. So, Mayuri, do we have time for a couple of more use cases, or do we want to stop for question and answers?
You can wind up within 5 minutes. So till 10:15, you can continue, and then we can have 10 minutes for question and answers.
Okay, all right. So let me just quickly then touch upon some of the other areas. So in text analytics, again, one of the most common techniques that is becoming more and more popular is, I'm audible, right?
Yeah, you are audible. Vipin.
Okay, all right, yeah. So one of the most common techniques that is becoming more and more popular here in text analytics is a neural network or deep learning method called RNNs. Again, don't worry too much about the details here, but there are many variants of RNN that you will see. And this is a space that is again evolving very, very rapidly, and a lot of research is being done in this space. For those of you who are interested, one of the most recent successes of this technique is something called the GPT-3. Right, so it's a natural language generation algorithm by, I think, Fast AI. Uh, do go and look up about GPT-3 if you are interested in this space, and that is the powerful thing about GPT-3 is that it can generate text if you give it some amount of prompts, right, or starting phrases. And it is claimed that the text that it generates is so authentic that in many cases it is very difficult to distinguish whether it has been generated by a human or by a machine learning algorithm, right? Similar to the Turing test. So go do try it out, and if you think it works, start using it for some of your college projects and submissions also, maybe, right? So yeah, but yeah, do give it a look, because it is something that is that was in the news very recently, and it is an area where things are evolving very fast. One of the use cases that I would like to touch upon over here is in terms of the due diligence, which many of these banks do in terms of uh, assessing their high net worth individuals who are going to invest huge amount of money in their banks, right? The bank is going to get into a long-term relationship with these HNI individuals. They don't want to get associated with people who have bad press, who have political exposure, or who have any litigation or sanctions against their names. So we had used a lot of these NLP techniques in terms of automating that process and bringing it down from like 3 weeks that humans used to take to about 3 days using this method. And we did that drastically by reducing the amount of documents that humans would have to evaluate um, when they are trying to find out information about these HNIs. So I don't want to go into the details of each step over here, but yeah, let me know, and maybe if you want more details, we can talk about it in the Q&A. With regards to speech, it is essentially, as I mentioned, not just about the audio analysis, but this is shaping up more and more in terms of conversation systems per se. And conversation systems have 3 or 4 broad key components. So one of the primary component is the conversation APIs, and they are available in all the clouds that you go. So if you go to GCP, if you go to AWS, if you go to Microsoft Azure, you will invariably find a conversation API there. If you go to IBM, there is Watson Conversations there as well. And then there are some of the non-cloud providers like IPsoft. So what are these conversation APIs? So essentially, these are APIs which can be programmed uh, to do text-based question and answer, right? So you type a question, it goes to these conversation APIs. There is a model behind the conversation API that has been trained. It will understand your question, the intent of your question. It will pick the most appropriate answer and send it back to you as an API JSON response, which then you can populate onto your chat box. So these are the foundations of conversation APIs, but they are now more and more being wrapped around with speech to text APIs. So the good thing about it is, like, for example, Alexa or Siri first listens to your voice, it converts that voice into a text field using speech to text methods, which is speech analytics. And then that text is sent to conversation APIs to get the corresponding answer. Answer comes back to your device, and then you do a text to and that voice is played back to you in the voice of an Alexa or a Siri avatar, right? So that's how the speech APIs and conversation APIs work in tandem. Uh, Slight advancement towards that is that nowadays we are working on engagements where this is getting integrated into telephony systems. So you call up any call center, you don't have to go through the IVRs, you don't have to go through a long wait queue, but there would be these speech or AI agents that would try to understand what you're saying, convert it into text, try to get you the answer, play it back to you, see if that is the answer that you're looking for. If you are convinced, you can keep the phone down, and many a times people don't even realize that they have spoken to an AI avatar, except for maybe the very robotic tone. But if the answer is not correct, then it gives you an option to get connected to a human agent, and then you go through the regular process. So that is where telephony systems like Nuance and Genesis are getting on or implementing these kind of speech and conversation systems. And then all the above three need to be supported by what we call conversation platforms. And those conversation platforms are systems which actually decide when the transfer should happen from an AI bot or an AI agent to a human agent. And when that transfer happens, all the information that has been collected before by the AI agent needs to be transferred to the human agent so that the human agent doesn't repeat the same questions and become very irritating to the customer who is calling, right? So essentially, that is what is one of the most popular technologies or use cases that is shaping up on the speech and conversation front. Uh, this is a quick representation of how we are building most of these call center or contact center transformation. I kind of covered that earlier, where the customer is trying to call on any of these devices, which could be phone, PC, tablet. It gets it hits one of the speech to text APIs and then gets converted into text. A lot of analysis of the text happens, answer is then sent back to the human agent. If there is any process that needs to be triggered, that gets triggered in the back end, right? So again, a quick overview of some of the use cases on the speech side. I'll just have two more slides that I will leave you with. One is with regards to what's there in the future, right? In the near term, mid term, and long term. I don't want to list too many things here because that list can be infinite and never ending. But the way I see it, in the immediate future, there are two things that will drive development in the AI space. One is auto ML, where a lot of these deep learning model building exercise will be automated by many of the vendors like Microsoft and Google. So you as a data scientist will have very simplified tools and techniques to build deep learning models. A lot of that heavy lifting and complexity of model search and model optimization would be done by platform providers. The second most popular thing I feel in the near term would be scaling of AI to large scale systems or production grade systems. In many use cases, that is still a challenge, and a lot of work is going on in that space. Cloud computing is one of the great enablers towards scaling AI. And now we are doing a lot of research in terms of seeing how we can leverage containers, Kubernetes, and many of those cloud technologies in terms of scaling up AI. In the medium term, as I said, natural language generation is going to be a key player or a key topic in news. So stay tuned to that. There may be some advancements on the image space as well, but I think image is a lot mature when compared to natural language generation. So in the medium term, I think that would be a good area of research. And in the very long term, probably 5, 7, 10 years down the line, there would be influences of quantum computing in AI, where many of these models can be trained a lot more faster and they can start doing a lot more complicated tasks using the supercomputing power of quantum as opposed to classic computing. Right? So that's about the future. In terms of some of the resources, the ones that I typically keep frequenting on a daily basis, there is a site called Archive where a lot of research papers get published. So if there are some of you who is interested in masters or PhD and so on, you would already be familiar with Archive. But there is a variant of Archive called Archive Sanity, which is where most of the machine learning and deep learning related papers get curated and published. And then it also has tabs which tell you which are the top trending papers, which are the most popular papers, and so on. So if you just want to go there and read what is the most recent research, this is a good place. Papers with Code is another website where many of the archive research papers are implemented by developers in Python and R and so on. And then they publish it for developers around the world to just explore and see. So that's another interesting place if you want to see how research algorithms get implemented, or if you want to implement your own deep learning algorithms. And then Kaggle Kaggle and Analytics Vidya, both are general knowledge sources for machine learning and deep learning related topics. They also hold a lot of competitions, and Kaggle score is a very industry renowned score, right? So if you are a Kaggle Supermaster or something of that sort, then that would carry some weight in your CV if somebody is trying to recruit a data scientist. So go there, and there are also competitions which are at a very beginner level to get you started also. So go there and try it out and see if you find anything interesting in that space, right? So with that, I'll stop and I will pass it on to you, Mayuri, for any questions that the participants will have.
Yeah, students, if you have any questions, then you may ask, please.
Yes, sir. So I have a quick question. What is the technology stack that you would recommend beginners like us should be learning in order to get a good start in the AI and ML industry, given that college coursework is often not up to date to current technologies?
So earlier, maybe 10 years back, I would have said R, but as of today, Python invariably is the most popular platform for building machine learning algorithms. In Python itself, there are levels or grades, right? There are basic packages like NumPy and Pandas that allow you to do some simple, sorry, a simple data manipulation. You can start with that. Then you move on to something like scikit-learn, which has some of those classic machine learning algorithms like regression, decision trees, and so on. You can try those. If you want to go one level higher, then you can go into TensorFlow. Abstracted version of that would be Keras. Then there are APIs like, I think it is FastAI. There is PyTorch from FastAI. So there are those kind of libraries which allow you to do a lot of deep learning models. So that's the stack which I would use for building my model. And then there's this whole new question of deploying your model, where you can look at various applications like Flask in Python to deploy your model as web services, or Django and APIs like that, right? Or packages like that. So that's from a ground up model development. But as I mentioned, there will already be models that are available which you can use and customize. So go and look at those. Go and look at papers for code. It may be slightly more complicated for beginners, but once you have reached some maturity, do go there and see how certain implementations can happen. There are courses that are available in Coursera, extremely expensive. You can go there and see also in terms of how you can start building models ground up. But I don't think it is worth the price, especially for people like us in India and other countries, right, where the quality of education and the resources that we get is way higher, and the support that we get is way higher. So I think for us it is slightly on the expensive side, especially for the student fraternity. Now, that is with regards to the open source APIs that are available, but you can always go to cloud service providers like AWS, or Azure or GCP, or even IBM. There are already available APIs or platforms like Watson Studio, SageMaker. They provide you a very user interface friendly platforms to build your model. To some extent, it may be free, but after some time, you may have to start paying some amount of money if you want to use it on a continued basis. But I think if you want to just try it out to a certain tier, it may be free. So those are some of the initial places where I would start. Okay.
Any other question from anyone else?
So either it was very clear or it was very fast.
Clear. Okay.
Sir, I have a question.
Yeah.
Sir, where can we like practice? Like for this, we would be requiring some some good amount of practice. So from like, where can we practice this?
So a very good question. There are, I mean, the reason why I said very good question is because there is a varying level of complexity for the models that you build, right? Uh, for beginners, you can start it on your laptop or any of the systems or servers that are available in your college itself. Now, certain colleges do provide GPUs, but I'm sure most of the colleges don't because it is slightly on the expensive side.
We
So
have.
when you have, right? Okay, awesome. So in that case, I think even when your model becomes slightly more complex, you can move on from a CPU-based model to GPU-based models, and that will allow you to build more and more complicated models and more deep learning-based models on huge set of data sets, right? So you don't have to go anywhere outside in terms of infrastructure for the beginner level that you are currently, right? But then if you are planning to have your own startup while you are in college and things like that, you can always get on to AWS or Azure or Google, and they have a good amount of images available there which you can subscribe to, and many of them are very cheap also, right? So if you go to AWS, I think for $1 you get 1 hour of GPU time, 1 hour of GPU time. So you can then use those infrastructure to build your model if it is something that you are trying to do outside of your academics as a startup or something of that sort. But otherwise, basic models on your laptop home system, slightly more complex and involved models on your college resources using GPUs, and then as and when it gets more and more complex, you can move to cloud. Did that answer your question?
Yes, sir.
And another platform might also be, there is a platform on Google Colab. They have something called TPUs, and they have ready-made notebooks and things like that also. So both to Ninad as well as Tejaswini, that's also a good place to start on Google Colabs. There is a free tier there as well. And one of the other important packages that I would recommend in terms or important technology stack component that I would recommend if you are starting machine learning is the Jupyter notebooks. So get familiar with the Jupyter notebooks as well, because a lot of these machine learning code gets exchanged as notebooks, especially if it's in the research space. So that's another thing that you can start looking at.
Yeah, so thank you very much, Vipin, for a very informative session.
My pleasure.
We really enjoyed your presentation as every small concept was discussed and explained with real examples or applications for better understanding.
Thank you.
And your delivery was really engaging. You brought new insights on AI to us from current work in industry. So on behalf of Computer Engineering Department, I sincerely thank you for accepting our invitation and imparting your expertise knowledge on evolution of AI and standard methodology for ML engagements along with real examples, business challenges, and some very good case studies from your company. Thank you very much.
Thanks a lot, Mayuri. It was a pleasure talking to this group and excellent interaction. Thanks a lot for this opportunity. And thanks a lot for all the participants for their patience and some great questions. Thank you.
Thank you, everyone.
All right.
Yeah.
So can we close the call then?
Yeah. Can we close this call now?
Okay. All right. See you then. You guys have a
Yeah.
great day ahead and great
Yeah.
holidays.
Same to you, Vipin. Same to you.
Thank you.
Bye. See you.